tell that it wasn't one of them. Hmm? Oh, shit. I love her. Feels also Anya is going.
Yeah.
Help out.
He wasn't listening.
He was not.
Anya is here.
Okay.
He's just in live.
So as for today, like I said, we're transitioning into the more mathy algebra level, all right, the nitty gritty. And we do this basically most of the rest of the semester. So polynomials, all right, which is basically just a bunch of, it has official definition we'll look at. But it's basically just a bunch of variables with powers of x's. In order to do this, we need to refresh on our rules of exponents and how exponents work. The main rule, when you have the same base, that's the big number, all right? And you're multiplying that by the same base with some exponent, same base, raised to some exponent, you can add the exponents. That is by far the biggest rule that we investigate. When you do this, you need to be careful not to multiply the bases. So 2 to the 3 times 2 to the 5, that is not 4 to the 8, that actually equals 2 to the 8. Because it's super important to understand what an exponent is. 2 to the 3, that means 2 times 2 times 2. An exponent is a way to simplify us writing multiplication a bunch of times. The other one is kind of a handwriting thing. 5 to the 12th, big base, small exponent. Way too often I see, all right, that drops down. And so the important part is don't drop the exponent and all of a sudden I see people writing 5 times 12. Make sure that you can read your own handwriting when you have those values. And then exponents do not rainbow. 7 plus 3 to the 3rd power. In order to actually simplify this, I have to do PEMDAS. What's the first part of PEMDAS? Parenthesis. This actually becomes 10 to the 3rd. And so, again, everything, when we start putting variables in there, people they forget that all those variables represent a number. Similar to the addition rule for the product rule for exponents, the quotient rule. Multiplying the same base with exponents becomes adding, dividing simply becomes subtracting. We're going to look at examples for all these. And then there are some other subtle ones as well, that if things are being multiplied, all right, the exponent can go into each piece, multiplied, not added. Exponent to an exponent, power to a power ends up multiplying. And then, right, same thing with multiplying and dividing. The exponent can go into both the numerator and the denominator. So these rules of exponents, we have to track piece by piece. Same base is the big thing, and those are the ones where we can simplify them down. So if I have 5a to the 12th, 5a to the 4th, that's division, which means I'm using the quotient rule. I can put those into the same, all right? I can bring the denominator up, and that was 12 on the top. Since that's being divided, then it's simply just subtraction. So I have 5a 12 minus 4, which becomes 5a to the 8. And I could leave it like that, but let's use one last rule, specifically this guy here. And then actually I can even rewrite that as 5 to the 8, a to the 8. Now, you can put 5 to the 8th in your calculator and then find whatever number that is, but that ends up, these numbers get very, very big unless it's like a 2 or a 3 as your base. Most of the time, and your base is low and your exponent is low, most of the time you can just leave it as 5 to the 8 power. All right, 0 is a special one. 19 to the 0 power, I can, go ahead.
0.
And it's not 0. Let's actually rewrite that as 19, 1 minus 1. Right? 1 minus 1 is 0. Then reversing, all right, the quotient rule, that actually becomes 19 to the first all over 19 to the first. What's anything over itself? 1. So anything to the 0 power is 1. It doesn't matter what is inside there. If the whole thing is raised to the 0, it is always just 1. Similarly, 10 to the 5th all over 10 to the 5th.
No.
1.
10 to 1.
The same thing over itself, right? Just because we're writing that complicated doesn't mean it is complicated. Anything divided by its exact self. All right, 7 squared to the 4th. All right, so that's this guy, power to a power. That means you have 7, 2 times 4, which becomes 7 to the 8 power. So exponent raised to another exponent means just multiply those exponents. There are a sum total of 5 rules here, all right? But those 5 rules can be used, all right, lots of different ways. Same thing again, anything to an exponent. And here's the big part here. Let's write this out one more time. If it's not mentioned, so I clearly have 2x squared, okay? So I have 2, and then I have x to the squared power. What power is this 2 raised to?
1.
1. If it is not specified, it is to the first power, right? Just by saying 5, that's technically 5 to the first power. Just like when we have an x, there's always a hidden 1 out in front of it. Then this follows the same rules as multiplying exponents. So I have 2, 1 times 3, x, 2 times 3. So if the exponent isn't specified, there's a hidden 1 in there. And so that becomes 2 cubed, x to the 6th. And I could absolutely leave it like that. This is what I was talking about. When you have low numbers, this is what I can actually do. 2 times 2 times 2, aka 2 to the 3 is actually what number?
8.
8. So I could write this 8x to the 6th. And either of these are correct. Depends if you want to go one more step or not. I wrote that way because my math lab gets kind of particular and it likes you to solve it all the way down unless it specifies leave it as exponents. So you want to make sure that you can do it either way. Okay, so once again, I have 5. Let's write this out with our exponents. Y to the 4th, that's y to the 4th power. 5 to the what power? First. Then, once again, I can multiply that 3 into both the numerator and the denominator exponents. And so 5 to the 1 times 3 is just 5 to the 3rd. And then y to the 12th. And again, that's perfectly fine to leave it right there. 5 times 5 times 5 is actually 125. So I could go one more step just to make the number nicer. And again, only when the numbers are low do I even bother going further. Once again, the best ones are when we have the same basis. A minus b to the 4th, a minus b to the 3rd. That a minus b, that entire piece is the base, which means I can bring the denominator up to the numerator. This is the quotient rule. All right, so I have 4 in the numerator, 3 in the denominator. What do I do with those two numbers? Subtract them. Which means I have a minus b to the 1st power, which means I only need to write that as a minus b. So notice all the parentheses can go away there because the whole thing, the 1st power, just means it's itself. All right, and one more time. So I have a division, and the big thing here is with the negative. So when I'm bringing that 4 in, so in the numerator, I clearly have a to the 3 times 4. In the denominator, bring it in one piece at a time. And that negative, all right, keep that with your number. That's -2. So that's -2. And what power was that?
4.
Not the outside. What power is the -2 on the inside?
1.
1. That means that's 1 times 4. And then b to the 5 times 4. Simplify that guy down. I have a to the 12th all over. Let's do b to the 20th. That one's easy. Then I have -2 to the 4th power. So with a negative, remember how negatives work when you multiply them. Negative times a negative becomes
Positive.
times another negative
Negative.
times another negative.
Positive.
So that whole thing, all right, the sign actually can be dropped there because when it's an even power, right, the negatives will become positive. When it's an odd power, it will remain negative. So I can leave that as 2 to the 4th or 2 to the 4th, what is that, 16? So I could write that as one more step, but since I'm out of space. So working with the variables actually becomes easier. The biggest trick almost always is dealing with that negative, but again, if it's an even power, all right, it'll go away, all right, it'll become positive. If it's an odd power, it will remain negative. We were making all our exponents positive there, and that usually is our main goal. Just like with the quotient rule, when you have a negative exponent, that actually means, all right, it's on the wrong side of the fraction. So we were bringing them up and they were all ending up positive, but I can do the opposite. If I have a negative in the numerator, I can move it to the other side of the fraction to become positive and vice versa. All of these are basically saying the same thing. We typically like to write our exponents using positive values. We don't like to have negative exponents because 5 to the -2 doesn't actually mean anything. 5 squared, I know what that is. So always flip your negative exponents across the fraction, all right, in order to make them positive. And all 3 of those rules say the same thing. They're all summarized basically in the first rule. So 81 to the -1. That means that's currently, the whole thing is over 1. If I move it into the denominator, that becomes 81, 1 over 81 to the 1st power. And I can drop anything to the 1st power, means that is simply just 1 over 81. So negative exponents, when you move them across the fraction, either numerator to denominator or denominator to numerator, all right, you will be changing the signs of the exponents. And this is basically just a subset. This is still summarized really in the quotient rule. Because in the quotient rule, if our numerator value is just a 1 and this one is a 5, it will end up being negative. So you can do this however you want to simplify. You can move it all to the numerator and then fix your exponent signs, or you can kind of just do the difference. So one piece at a time, just looking at the A's. All right. If I have a negative in the numerator and a positive in the denominator, should I be moving them up or down? Down, right? Because if I move them down, I now have a to the 5th, a to the 8th. So that b in the numerator, what power is that?
1.
1. So this is the same thing. They're both positive, but if I want them to result in positive, should I move the b to the 8 up or the b to the 1 down? Down, same thing. You move it to the bigger number. So that becomes b to the -1, b to the 8, and now all that's left in the numerator is a 1. This is not the only way to do it. It's whatever approach you can subtract or initially. I'm just doing this slowly here. So now I have a to the 5th, a to the 8th. When I have the same base, what can I do to the exponents?
Add them.
Add them. So now that becomes a to the 5 plus 8. Same thing, b to the -1 plus 8. So I have a to the 13th, b to the 7th. And here's the big thing, the instructions, all right? Express using positive exponents, all right? At the end, you don't want to end up with negative exponents. We want them always positive. When you have it to a negative exponent, the easiest step is to multiply that negative exponent in and then deal with making the negatives positive. So I have x to the 4th times -3, 2 to the 1st times -3, y to the 1st times -3. So power to a power, multiply that in each step. Okay, so we just did the multiplication of the exponent through to each piece. And then in order to make them positive, actually, this is pretty nice. If everything is negative, that means that x is where's that going?
Wrong.
And what about the 2 and the y?
Well,
Yeah, so they're actually just flipping. Be aware, that's exactly what this property says. All right, it says that you can just flip the fraction. So again, you can speed yourself up, or you can just do it one step at a time, whatever is easier for you. But that means the 2 goes up, the y is going to go up and become positive, and the x is going to go down and become positive. And now I have everything expressed in positive exponents. That is perfectly fine. I could leave it right there, but we already identified 2 to the 3rd is 8. So again, I can leave it here. That's absolutely fine, or here, whichever, whenever possible, I like to reduce the number of exponents because we just have a lot going on. Similarly, 4 to the -2. Remember, that is 4 to the -2 over 1, which means the only thing to be done there, all right, is to move that across the fraction to become a positive exponent. And then what's 4 squared? 16, which means that's 1/16. And this is about how we understand numbers, right? A negative exponent means the same as 1/16, but I'm pretty sure most people have a better understanding of what 1/16 is than 4 to the negative 2. So our goal is always to get it into what is most understandable. And that's all an exponent is, right? It's something that looks complicated, but is something you're actually quite familiar with. So also knowing when there's a lot to do or not much to do. What are we gonna do with this 5?
Back to the 1.
Move it down?
No,
No?
the X -7 now, right?
Yeah, there's nothing to be done with that 5. What about the y squared? I'm gonna leave that as well. The only thing to actually be messed with here at all is this. I'm gonna move that x down and that z up. So we also don't, knowing when to stop is important and knowing not to mess with things. That 5 and that 5 over y squared, there's nothing to do there. So that z is gonna move up, which becomes z to the 4th. Y, just because x comes before y. X to the 7th, y squared. That's it, right? There's nothing else to do. So knowing when to stop, all right, is crucially important. And I know it's like, wait, I didn't get x equals 7. Yeah, that's not what we're doing here. We are simplifying. Notice the instructions, okay? Expresses using positive exponents, all right? Simplify. We are not solving equations at the moment. We are just simplifying expressions. All right. When we have a lot more things going on, deal with them one piece at a time. Deal with the numbers, then one variable, then the next variable, then the next variable. All right. So even though it looks like a lot's going on, one thing at a time. -10 divided by 5. -2, right? I was like, it is that simple. X to the -3, divided by x squared. All right, now I think it's easier to immediately bring this down. So that means I have in the denominator, I have a 2. And if I bring the -3 down, that becomes then
5.
+3. Add that, that becomes x to the 5th. All right, similarly, I have y to the 1st power and a y to the 5, which means that's going to end up on the denominator. And that ends up being y to what power?
4th.
4th. Does everyone see how we can do that quicker? You want me to do that slower?
Oh, no, you're good.
Actually,
4th.
I will do that just a little bit slower.
Cool.
X to the 2 minus -3. All right, that -3 is coming down. Y to the 5 minus 1. So the -3 came down, and it's always subtraction, so it's 2 minus -3, which will become positive. The 1 came down, flipping its sign from positive to negative. When you have this, and make sure it's the same base, and everything is being multiplied. All right, notice that there is no addition occurring amongst the variables here. So that's the biggest thing about all these. Everything is being multiplied. If this said x divided by x to the 5th plus y, you can't do anything. That's as far as I can go with that. Okay, I can't bring that x down. always, and if you ever get confused, replace your variables with numbers. Because again, and the easiest number with exponents is always gonna be 2s and 3s, right? X becomes 2, Y becomes 3. Make sure that when you plug those in with what you started with and what you finished with, those result in the same thing. Don't use 0 or 1. Those are special numbers, all right? So 2s and 3s, 2s, 3, 4, like keep it as low as possible.
How does that 2 minus -3 become 5? Do you add it?
Well, yes. Negative, negative always becomes positive. Yes,
We're not multiplying it, so is it just different for this?
we're not multiplying it.
So then it wouldn't be like a,
That is just this piece, right?
Yeah.
So if I was to write that out, when that goes down, the x squared is still there, and that becomes x, flip the sign. So I was writing it as negative, negative,
okay,
just to emphasize that it's becoming a positive.
thanks.
How did you get -2?
Negative, oh, -10 divided by 5.
How are we gonna get rid of the -2 so that it's positive?
Positive exponents. What power is that -2?
To the positive one.
It is to
The first power. Positive exponents, all right? Yes, you can end up with negatives, of course you can, all right? But no negative exponents. All right, so all my exponents there, 1, 4, and 5, those are all positive numbers. There is no way to get rid of, the negative. One big application of exponents is scientific notation. Scientific notation is best when dealing with very, very large numbers and very, very small numbers. If you have a number with 10 zeros, the decimal, then 10 zeros, scientific notation is a better way to write that. All right, and that's what I have written here. So scientific notation is the number, all right, a single value between 1 and 9, all right? 2 to 10 decimals, doesn't really matter, all right? And then the exponent turns that into, all right, the actual value. So 452, I can actually represent as 4.52 times 10 squared, right? Because that's actually times 100, which becomes that. Negative exponents, all right, you can't get rid of them in scientific notation, all right? So notice this doesn't say write as a positive exponent unless I want to write it as a fraction. But that represents decimals. So as the numbers get smaller, the negative exponent becomes larger. As the number gets larger, the positive exponent becomes larger. That's also good for the math because when doing math with scientific notation, you actually can break this up into each individual piece. 1.8, all right, ignoring the scientific notation times 10 part, and 2.3. I can multiply 1.8 and 2.3 times 10, and then I can combine using the rules of exponents. To the 9th power and to the -4th power, what do I do with these exponents? Add them. So that becomes 9 minus 4, because I'm adding a negative. And then I need to. Whatever that becomes. So you can actually, with scientific notation, you can break it up into the number value and the 10 to the power of whatever value. Same thing with the division. 3.41 divided by 1.1 times 10 to the 5. And if I'm dividing by -3, if I bring that up, what am I actually doing?
Adding.
Adding. 5 minus -3. And this is really, really nice with scientific notation. Now, be aware, your calculator does this, okay? So you can put this entire equation into your calculator, all right, using the scientific notation button. It is second log, the button to the left of the 7. Oh, that one right here, go. I was like, so your calculator actually can hold scientific notation, and you can do that whole command within your calculator. When you have numbers, it always is a good thing to use your calculator. The important thing is in the calculator, it would come out as 3.1, right? Then it says E8. So your calculator would spit out this output. What do you think the E stands for? Exponent. It's saying, turn this into scientific notation, all right? So as long as you understand that this converts into scientific notation, I was like, when you have numbers, use your calculator. But this is what your calculator is doing. It is doing these exact commands. Everyone with me with the input? And important, when inputting in your calculator, parentheses everywhere, right? That's the big part. Your calculator only knows what you type. It doesn't know what you mean to type or what you're intending, right? It only knows exact output. Did we get it? Get it? I just want to make sure that scientific notation is one of the best things that the calculator can shortcut you to do. We get it? We done it?
Where's it at? I was sorry.
And this is the nice part. So that button times 10 to the.
Which one's it?
So second log.
Got you.
And see right there where it says 10 to the,
Yeah.
so that's the scientific notation button.
Thank you.
Okay. Yes, you have an X. Oh, here it is. It's right here. Yeah, yours is the same. So 3.41 times second log 10 to the fifth. Okay, so with you, no equals then divide by. Well, so we're doing 1.1 times 10 to the. Okay, your mode, there we go. Okay, so 3.1, and look, yours even says times 10 to the 0.8. Okay, the annoying thing about. Yeah, make sure.
Oh, yeah,
Google
yeah.
how to use that.
I know how to use it. I use it all the time in chemistry, all this stuff.
All right, excellent. Yes, so scientific notation, very, very nice. Be aware that this is your calculator output. Never, ever, ever, ever write this. You write this as scientific notation. This is calculator output. Our goal, all right, in the real world is to translate computer output to human output, all right? Scientific notation is very, very well known. Calculator output is junk. That means it needs translating, all right? This is wrong. That is wrong.
So right.
So wrong, because that is just, you are not computers, neither is anyone else. Okay. Last little bit. So finally, polynomials. Polynomials are going to be all about using all those rules of exponents. But in order to determine what a polynomial is, we need now the official definition. So the official definition of a polynomial, all right, a function with variables raised to non-negative integer powers. So that's why we needed to make sure we're on board with what a negative power represents. And then the highest power of a polynomial, all right, of whatever power of the variable, all right, that is what is known as the degree of the polynomial. So let's look at a couple examples and identify what is and is not a polynomial and what the degree if it is a polynomial. All right, so for this guy, you can have all kinds of mess with the coefficients. So I have here, the coefficients are 5, -3, 1/2, and -2 plus I. That's fine. The polynomial part is referring to the variables. X to the 4th, x squared, x to what power?
1.
And x to what power here?
0.
0. All right, x to the 0 power, is 0 a non-negative number?
Yeah.
Yes, because 0 is neither negative nor positive. That's why it's important in the definition, non-negative integers. All right, so, all right, this is absolutely fine. So I see non-negative, all right, exponent powers of the variable. That makes this a polynomial. What is the highest power? 4. And that's the degree. All right, for the next one. I have x to the 5th. All right, that one seems okay. What's the power of x on for the -1 here?
0.
0, x to the 0 power. Okay, now here's the weird part, square root. Does anyone know what power a radical actually represents?
-2.
That's not negative.
All of them are.
Square root, which means what number is attached right here on the radical? 2. All right, if this is a power of 1 on the inside, this is actually to the 1/2 power. So, does that mean if this is x to the 1/2 power, is that a non-negative integer?
Yes.
Yeah, it's definitely non-negative because 1/2 is positive.
But isn't an integer a whole number?
An integer, all right, is 1, 2, 3. Technically, integers are negatives and positives, but we're specifically identifying non-negative, which means this has to be a positive or zero or positive whole number, which means this is not a polynomial. All right, for this guy. This is being multiplied. Now, polynomials are typically are multiplied out. And we're going to talk about multiplying this out in a bit. But if it's positive if this is the power of 1, this is a power of 1, this is a power of 1. When it multiplies out, when you're multiplying exponents, what are you doing with those exponents? Adding them. All right, that's not going to change the sign. So are these all non-negative integer powers of x? Yes. So this is a polynomial.
And then the degree would just be 1.
The degree is the tricky part here.
So you have to distribute it.
We would have to completely rainbow and multiply this out, but we can do that kind of fast. The degree is just the highest power, so I don't care about all the other ones. If I have x and an x and an x, that's a power 1, 1, 1. And guess what the degree is? 3. You can simply just add the powers of each of the exponents. So that's the only hard part on that one. And mostly, you want to know that, yes, I could rainbow and box and multiply that all out, but why take the time? Just look, 1, 1, 1, add them together. So doing that quickly is the big part. All right. For this last one, I have 7 x to the 3rd. Okay, is that a non-negative integer power? Yes. Then I have 5 over x squared. Is that a non-negative integer power?
Is -2?
In order to be a polynomial, it has to be written, all right, all in the numerator. It doesn't say that in the definition, okay, but that's the important part because 1/x² is just a fancy way of writing x to the what power?
-2.
-2. All right, so it all needs to be written, all right, on one line. Basically, which means that this is not a polynomial because I have a negative integer power there. And that is exactly what we were just talking about. And that's the biggest thing that stops it from being a polynomial and the thing that people miss because the way it's written, it looks like, oh, I have all non-negative integers, right? But that's in the denominator, right? Which violates the definition of polynomials.
So go back to the first one. Can we just like do 5 to the first power and would it still be 5?
5 to the first, just the 5 value?
Well, instead of putting 5 to the 0 power.
That's just to 5.
Oh, okay.
5 is equivalent to 5 to the x to the 0 power, right? Which is 5 times 1. All of those mean the same. I was just identifying that there is a quote x in there because there's always an x to the 0 power everywhere, right? There's also a 932 to the 0 power everywhere, right? The 0 power, I was just emphasizing that is a non-negative power. So by definition, the number 5, that's a polynomial. All right, doesn't have any x's in it, all right, which makes it's kind of a boring polynomial, but that is a polynomial because it's x to the 0 power.
The degree would be 0.
And the degree would be 0. That is exactly correct. All right, one last little note. When we write out polynomials, and we're going to go into this more extensively next time, we write it in descending order, all right? These problems were not written in descending order, but that means you start with the highest degree and then write them 5th power, 4th power, 3rd power, all right, as cleanly as you can. None of these really are nice polynomials. As we investigate, that's going to be the biggest thing. This also I wanted to identify because this is going to be instructions in both on the upcoming quizzes, activities, and home fun. All right. We okay? Any questions, concerns? All right, as always, I have a wonderful activity for you to investigate, all right, and take a look at.
Pretty old pal.